Okay, so the first thing that I was going to do was to remind you a little bit the problem we were discussing, just because there's like a lot of stuff that, of useful properties that you can extract from that example that we were doing with the farmer. So that's where I'll begin. Let me see if I can connect the HDMI. Well, I don't know if you had like a chance to read the PDF I wrote about the farmer's problem, but it was just a little bit. I'll go over it first just to kind of like explain what I was trying to do near the end. But well, maybe one of you found the answer and you can tell me if you found it. But I'll kind of go over that again. Okay. Uh, so why does this look so weird? So why is this weird? Now it's better, I guess. Let me see. Stop sharing. This works now. Okay, I think it does look better now. So let me put in do not disturb my computer. By the way, I think since like after today's class, we will have covered like at least some interesting material. I will write like a list of problems for you to work on. And I'll ask you to like upload the solutions to a selection of those. But I'll have that done before the end of the week. So I'll kind of like have like write a list for you to like of problems for you to kind of get it more like acquainted to like the type of thing that is like interesting like in asking you. Um, but yeah, like I'll hope to have that done like maybe tomorrow or like Thursday the latest. Um, okay, so what was the idea of like the problem we were discussing? So I don't know if you remember like the entire setup, but we had like like some amount of like seeds for potatoes and some amount for like carrot seeds, and we're trying to make as much money as possible. And like just because of the price like that you would get paid for like the potatoes or the carrots, we ended up having something like this where we were trying to find the max of this function. Right, I think X1 was the amount of like potato seeds and X2 the amount of like carrot seeds you would grow. Okay. So we ended up like trying like the original problem was like we were trying to find the max of that function. And again, like whenever you're trying to find the max of a function like this, the idea is that you want conditions on what values the variables can take, because otherwise like the problem is not too interesting. So in this case, like the two conditions, kind of like natural conditions, were that each of the variables should be non-negative because they represent like the amount of seeds that you're going to grow. And most of the problems, 99% of the problems will have these conditions kind of baked in. Like we will always work with non-negative variables. In fact, there's like probably next time or like not next time, but like soon I'll teach you like there's a trick that you can do to kind of like rewrite these things in a standard way. But it is not like a too much of an assumption to just like assume that like the variables are non-negative. That's kind of like the most natural things in most realistic problems. Um, What's a little bit more specific to each problem are the extra conditions. So the first extra condition was that the amount of seeds, the amount of potato seeds you could grow were 3,000 kilograms. The second condition was that the amount of carrot seeds you could grow, the most you could grow were 4,000 kilograms. And because you had like a certain amount of fertilizer equal to 5,000 kilograms, like these two together, seeds of like potatoes plus carrot seeds like cannot exceed 5,000. Okay. So we found the max to this problem geometrically because since it's only two variables, you can draw everything on the plane and you get this kind of like nice shape. And what I was telling you last time was that the shape correspond, like the corners is where the max could occur. Let's see, where do I have it here? Like I can just briefly remind you of how the shape looked like. Right, so that's kind of like the shape for like the region that we had, like that is where like all the inequalities were satisfied. And then the corners are the candidates for where the max or the mean could occur if you were had tried to find a mean, like kind of they both work the same way. Okay, so the solution that we found, the values that gave you the optimum or like the maximum were like 1,000 for the potatoes and 4,000 for the carrots. So that's kind of like where I spent like most of the time last time, and now I'm going to kind of like explain a little bit better what I was doing near the end of the class. But is that okay? Making sense up to this point? Are there any questions so far? So good. Okay. So the idea is that, okay, literally I solved the entire problem, right? And that's how I found the max. What I'm trying to do now is something a little bit different, which is like, imagine that, like, for whatever reason, like, I don't want to find the corners. Maybe I don't know how to draw the region of, like, of that satisfies these inequalities. So, oh, by the way, I forgot to write this, like, I'll update it on the PDF. And the max, the value for the max it was 1.2 times 1,000, right? Plus 1.7 times 4,000, which gives you 8,000, right? So $8,000 was the maximum amount that you could make in this problem by choosing like those values for the variables. So that's like the maximum. We already know the maximum. But so the kind of like the second stage, which is like what I was starting to discuss last time, is like was more like, imagine that I don't find the corners for whatever reason. So I just want to know if I just start playing with these inequalities, right? Just like from the inequalities alone, like algebraically, can I kind of like conclude that like the function, the most it can be is 8,000. So I'm trying to kind of like uh, give a bound for how big this can be just based on the inequalities. Without doing the picture. That's kind of like my point. So that's what I was trying to explain you last time. So what is one thing that you could do? Let's go again, like these inequalities are not that interesting. So let's just focus on the last three inequalities. Let's call them A, B, C, right? So, and let me write the function here so that you know why I'm choosing the coefficients in this way. So for example, like here's one thing I could do. I can take the first inequality, right? And then multiply both sides of the inequality by 1.2. Why by 1.2? Because 1.2 is literally what appears multiplying x1, right? So I can do 1.2 on both sides of A, right? If you multiply both sides of A by 1.2, you get 1.2 of x1 is less or equal to 3,600. Okay? And likewise, you could take the second inequality and now multiply it by 1.7. Why by 1.7? Because that is like the number in front of x2, right? So if you multiply the second inequality by 1.7, so you get 1.7 x2 on the left side, and then 1.7 times 4,000 should be 6,800. Okay, so far so good, everyone with me? So that is like just algebraically what you get from the first two inequalities. And as like you can add these two like inequalities, like the inequality is preserved, like they're both less or equal to. So if you just add like the left-hand sides of the sum should be less or equal to the right-hand sides of the sum. So like that's how you get 1.2 x1 plus 1.7 x2, and that gives you 10,400. Okay. So what that says, but what that says is like, based on this calculation, we know, even like, again, we have to pretend that we didn't know the answer. We know we could not have found like 11,000 as the answer, right? Because this is saying the most you could ever get to is like this number. Is that good? Is that okay? Now, And here comes like kind of like the game, because it's like, notice that to get to this bound, I only use like the first two inequalities. I kind of totally forgot about the last one. So like a more strategic way could be like, well, maybe you want to incorporate the third one. It does make sense that you would like to try to play with all of them. So how, and again, there could be more than one way to do it, but like, let me show you one thing that you could do. Uh, so I want to think of 1.2, it's kind of silly, but think of 1.2 as 0.2 plus 1, and think of 1.7 as 0.7 plus 1. Why do it that way? Because if I do it that way, then I'll multiply the first inequality by 0.2, right? So I get this. I'll multiply the second inequality by 0.7, so I get this, and I'll leave the third one alone. So I'll leave it like, or multiply by 1 if you would like. Okay. So that when I do it, like the idea is like you want to add up all the inequalities that you're working with. So if you add up all the inequalities, there's like a 1 here. So 1 plus 0.2 will give me 1.2, which is what we want. And 1 plus 0.7 will give me 1.7, which is what we want. So if you do the magic, like the algebra, you add all these three numbers on the right-hand side, and you get 8,400. So far, so good. Is that making sense what I just did? And so what that says is a lot better, because it says from the inequalities alone, I know it is a lot better like the number that we have found before, because like that was 10,000 something. What this is saying is like, actually, you could not have obtained something larger than 8,400. So now this kind of rules out getting paid $9,000, for example, right? Which makes sense, because we do know that the optimum was 8,000, right? But the idea is that now I'm looking at it, I'm trying to find that entirely from the inequalities without finding the corners, if you know what I mean. Is that kind of making sense? Like kind of like what I'm trying to do. So it's kind of like a, you know, an interesting question, whether you can just play with these inequalities to get 8,000, because we know that 8,000 is like the magical number, because that's like the max. So like the game, like, I don't know if anyone tried it, like, the game is like, well, can I multiply the first inequality by a number? I'll call it y1, and you'll see why in a moment. Can I multiply the second inequality by a number, which I'll call y2? And can I multiply the third inequality by a number, which I'll call y3, right? So that if you add, like, if you combine that together, right? If you combine that together, you get this inequality, okay? But the idea, right? What is the idea? Like, essentially, I want to know what is the smallest thing that this could become, because this is what it is controlling the amount of money I'm making, right? So you want this number to be as small as possible, okay? But these coefficients, like for these coefficients to be interesting, like they have to be related to these numbers, right? Like 1.2 and 1.7. So essentially what you want is at least this to be like 1.2 or more, and at least this to be 1.7 or more, because the moment that happens, then you can control like the function you were maximizing by these numbers. So essentially what I'm trying to say is that this is how I wrote it. And I'll return to the notes in a moment, but I just wanted to kind of like give you an idea, summarize what I wrote on the iPad. So essentially what you want to do is like, you want this to be actually as small as possible, because again, that's what it's telling you how much you're getting paid, from this perspective. Subject to these conditions, because again, like if you need positive numbers, because otherwise like the inequalities can get reversed and it's a mess. And then also these inequalities. Notice like in the previous two examples, I did it with like an equality. They were like the numbers that I chose literally added up to 1.2 and 1.7. So this is a little bit more of like a relaxed condition, but it's like useful to have. But the goal is kind of like to see, oh, how small could this become? And if possible, can you get it to become 8,000, which would be really cool. Is that, oh yeah, sorry. Oh, like, oh my God, like, did I do like the numbers wrong? Could be possible. Where is like, okay. So, okay. So like if I multiply everything correctly, I multiply this by 0.2, this one by 0.7, and this one by nothing, right? And then I add up the right-hand sides here. So these two give me 3,400, and this 5,000, this is fine, right? Like, again, otherwise it would have been a bit embarrassing. But yeah, like it seems like we're fine. The point is, again, maybe I should put this in colors, you know, like kind of like this is not too clever, right? So when you play when you use like the inequalities in not such a clever way, you got this number. When you do like the use like inequalities in a more clever way, you got 8,400, right? So the kind of like what I'm asking is, can I have chosen like different numbers right here to get actually to 8,000? And 8,000, because we know that that's kind of like the best, you can, like, for example, you cannot get 7,500. That wouldn't make sense because that we know that the max is 8,000. So you cannot go below the max. We're cheating a little bit because we already know the answer, but that's kind of like, it's kind of why it's kind of fun to look at it from that perspective. Yeah.
How did we get from line 9 to line 10?
Let's see. Okay, okay, okay. So the thing is like, these, like, the thing is like, you want, this is what you get when you multiply the inequalities by y1, y2, and y3, right? But you want this to, like, the idea of having this expression is to control, like, the quantity that you want to maximize, right? So let me put it like this, like, um, like what I'm trying to say is that what you like, oh, like, let me explain it this way. You can imagine that I had chosen, imagine I had chosen that y1 plus y3, like something silly, is 0.5, right? And what y2 plus y3 is 1, even, or yeah, 1, let's say. Then you would have 1.5 x1 plus x2, right? Um, you would have that here, right? How is that? What is the point of having that combination? Because how can you control this quantity, right? How would you be able to control this quantity with these coefficients, right? Like, at least you want like the coefficients here that you can get from the inequality to be as large as the ones that you have in here, because otherwise, like, there's no point, like, there's no point in doing this if you're going to get 0.5 x1, if that makes any sense, right? Like, you want at least the bound, that's like, maybe I should have like that's kind of what I'm trying to say here, like, you want this number to at least be smaller than the one that you're putting in the inequality, because otherwise how are you going to control it with a less or equal to? And likewise, you want this number to be as smaller than the one that you're getting from the inequalities, because otherwise there wouldn't be a way to control it. In the previous two examples, I actually kind of like did it on the nose, you know in the notation, like, in the notation here that I'm using now, they were literally adding up to those coefficients. I'm just saying that you don't need them to add up to the coefficients. You can be a little bit more flexible. You know, you at least need them to be larger than the coefficients, you see, because otherwise there's no way to control that. Is that making sense? Kind of like, did anyone try that problem? Oh, sorry, yeah. Did you find the value?
For y1, I got 0. For y2, I got 0.5. For y3, I got 1.2.
Yes, that's correct. So like for a y1, you got 0. For y2, 0.5. For y3, what was the value for y3? 1.2. Perfect. Okay. Now, I'll show you how these inequalities look. The thing is, like, these inequalities live in 3 dimensions, right? Because there are 3 variables. I'll show you how that looks. And it's a mess. So like, it's kind of like nice to see it one time so that you never see it again, because like you cannot pretend to see this every single time once you have more than 2 or 3 inequalities. Even when you have 3 inequalities, it's like a very cute picture, but it is kind of like messy. Like, it took me, when I did it like on algebra, it took me a while, because it's kind of confusing. Let's see, let's see. So here it is. So yeah, it's like, okay, let me see if I can explain it. Um, what were like, oh my, okay. So like what's happening here, which again is kind of like messy, but like let me see if I can say it in a way that makes sense. Um, Essentially, what are we seeing here? So my eraser. So like maybe it's better to switch to like the regular notation in terms of X, Y, and Z, like just for a second. So this would be X plus Z and 1.7 less or equal to Y plus Z. So that it matches what like you see on GeoGebra. And so, how would you interpret this, right? So it's kind of like a similar thing to what we did before. If you want to understand how this equation looks like, you would draw first the equality. But what is the equality? It's 1.2 equals X plus Z. Okay. And that is the equation of a plane. Okay. That is a plane in 3 dimensions. So it is one of these like tilted planes or slanted planes. In fact, this is like the one that moves in the y-axis. So these, I think I have there's so many things here. But the red one, the red plane is the one that corresponds, is the one that corresponds to this equation. And then this is like, let me see if I can zoom in. So the idea is like that you have to imagine that this goes forever. It's like if I had drawn all the planes, it's like a mess. But then the plane cuts like the space into two sides, and one of the sides satisfies the inequality. That's kind of how it works in the same way in which it works with lines. So like kind of like because this is like a greater equal to, you kind of are looking at this side of the plane. Again, like the picture itself is kind of complicated, so I just want you to like actually appreciate that it is a complicated picture more than like like the intrinsic details. The other one, like the other one, if you were to do it, that is another plane because there's no x. That just means like it moves like the same way along the x direction. So that's why it's the green one. And again, the inequality, because it's a greater or equal to, actually corresponds to this side of the space. And then these other regions that you see here kind of corresponds to like setting like the, you know, what, like x equals 0 or y equals 0 or z equals 0. So like they're kind of like 5 pieces to this picture, like let's see, blue, purple, red, green, what is it, like gray. So there are 5 colors. Each color corresponds to one of the equations, right? Because like again, there were like 5 inequalities if you go back to the notes. And then these planes can intersect at different points, which are like these corners that you see here. So I found the corners, and of the corners, I checked which one like gave me the minimum. Okay, so like the idea is like, the thing is like 2 planes intersecting a line. So I found the line of intersection, and then I intersected that with the planes. I did a couple of things to like, but like that's where you kind of like get the potential places where the mean could occur, and then you just check by trial and error where the mean happens. Okay, so but this is way harder like as a picture than like the picture that we had like last time. So of course, like the idea is not to do it this way, but it's still kind of like to emphasize that the minimum, it does happen at the corners. Okay, just in the same way in which before, like the max did happen at the corners as well. So it's more like to appreciate, the difference between the geometry and the algebra, because algebraically you kind of start playing with the equations. I don't know if that's what like you and the others did. You kind of like start intersecting the equations and see what you find, and that's how you get like the table of potential values. But geometrically, if you actually want to see what that looks like, it does require like some like skills, because it can be like a hard picture to to see. Is that making sense? So, but I'll kind of like explain why I was interested in kind of like see like doing this like in a moment. I just want to write some things on the iPad because I have set a bunch of stuff. So, but yeah, like this is like the point of like doing this picture is like okay, yeah, like the regions can get tricky, like like when you start asking where all the inequalities are satisfied, that actually can look like a more complicated than you could have expected, I guess. Okay, so let me explain why am I doing all of this. And so something really cool will happen once I write that things down on the board, on that notes. So essentially, just to summarize what I was doing, we were trying to like, well, I'll put it here, just see farmer's problem PDF for more details. But the idea is that we were trying to find the mean. So we were trying to find the mean of 3,000 y1 plus 4,000 y2 plus 5,000 y3 subject to those inequalities that let me write these inequalities first. You want zero, like you want y1 to be non-negative, you want y2 to be non-negative, you wanted y3 to be non-negative, and then like the interesting inequalities again were that y1 plus y3 had to be at least 1.2, and y2 plus y3 had to be at least 1.7. Okay, and if you go through this, all of no, again, like don't. If you were to find the corners for this region, I'll put like the list. If you try to find the corners, for this region, or the region that satisfies the inequality, you find that these values. You find that y1 could be 0, y2 could be 0, y3 could be 1.7. So that gives you the 0.001.7. And in that case, like the function equals, like the function gives what 8,500. Let's see. And then you could, or is this, wait. No, I think I meant 1.2 if I'm, wait. Oh, this is like, what am I doing? I'll fix that one in a second. I think I did something wrong there. Oh no, is it fine? Like, does that satisfy? Oh yeah, no, that one is fine actually. Sorry. So that's fine. Like that's fine. That does satisfy all the inequalities. If you, yeah, so that's fine. Then you could have this one that is like the one we were discussing. Also, those are like corners. Like the corners is essentially where three planes intersect in this case. Like the corners are where three of the five planes intersect. So that was one way to find it. But again, we will have like a more systematic way to find these things. So I'm not too interested in you kind of like noticing, like, how to find this problem this way. Like I'll give you a better way to do those things. Okay. Now get kind of comes like the climax of the class, because it's like, what's the point of doing this? Like, why did I want to, like, besides like fact that it maybe was like a slightly interesting question, why did I want to ask try to find this? Oh, by the way, I should mention explicitly that this is like the value of the max, right? This is the value of the max. Although I'll emphasize that a bit more in a moment. But kind of like, oh, sorry, yeah.
So we were finding the minimum, but we want to find the best bound.
Correct, yeah. Yes. But the kind of like the nice thing here is like the best bound happens to agree with like the max itself, right? Like, because I guess you could have imagined that just by playing with the inequalities, it is impossible to achieve 8,000 for some reason. But kind of like what this is saying is that no, like you should actually recover like the optimum value from like playing with the inequalities essentially, which is not super obvious actually. Yes.
So the, the best bounds don't always point to the max.
Well, like the cool thing, so that's actually what's called the strong duality theorem, which is it will say that when the bounds are finite, they will agree. That is what the results, like that is actually one of the big theorems of the class. I kind of like laying out the crumbs for it, although I'll write it more precisely later on. But what this says is that in fact, yeah, if this is going to have like a minimum, the minimum will agree with the maximum from the other problem. Yes, yeah. Well, and when like unless in silly cases where one is infinite and the other like yeah, like if they're both finite numbers, they have to match.
Okay.
Yeah, which is like a great theorem. Like it's actually why I'm doing this. Otherwise, I wouldn't do it. You know what I mean? Like if there were always a gap, actually, even if there's always like a gap, that's kind of interesting. But kind of like it's better than that. It's saying like the minimum that you'll find to this problem will agree with the maximum of the original problem, and that's called like the strong duality theorem. Like that's one of like the big piece. That is one of like the reasons why like this in like linear optimization stuff is interesting, kind of like kind of thing. But I'll write that in a few minutes, like actually, at least like verbally, because then we do want to write it in like a more mathematical way, but I don't want to do it right today because I'm still kind of like laying out like some of like ingredients that happen in in this course. So first, like I want to kind of like give more like a linear algebra question for why I'm doing this. So, and then I'll give like the second answer, which is like what I just said. Why am I doing this? Because let's think about the original problem. Okay, so let me write the original problem that we started with last time. And this is really like cool actually. So like in the original problem, it was you were trying to find the max of 1.2x plus 1.27 x2, right? And you needed x1 to be non-negative, you needed x2 to be non-negative. And then you wanted x1 to be less than 3,000, if I'm not mistaken. You wanted x2 to be less than 4,000. And then you wanted like the sum to be less than 5,000. Okay, oops, sorry. I always forget that this like thing doesn't really go well. So one of the things that I mentioned last time, if you remember, is that you could rewrite this in a more like fancy notation using vectors. right? Because the max here is like the dot product, right? So let me write that down in a more like linear algebra notation. So the max here could be this is like a dot product, right? It was a dot product with between what, like 1.2 comma 1.7 dot x1 comma x2, right? Like a dot product between these two vectors. And then, well, I can write it this way if you want. Like I can write like the first two inequalities, which I didn't do last time, but like it's like kind of like also nice to do like this. Again, like the first two like are kind of like not that interesting because they're kind of like baked into every single problem. And then the other one, like you can write it in matrix notation because there are like three inequalities, two variables, so that gives you a 3 by 2 matrix, right? Like 1, 0, 0, 1, and then 1, 1 times x1, x2 less or equal to 3,000, 4,000, 5,000. Right, so like which in this case I could call the matrix A, which again, like this matrix A is 3 by 2, this vector X, which is what, 2 by 1, and this vector, which is called B usually because like if you remember like linear algebra, like whenever you took it, you know, like usually like the systems of equations in linear algebra are written like AX equals B. So I'm just kind of trying to follow that notation, right? So it's essentially the same that you know, it is more or less the same idea. It's, instead of like an equal sign, there's like a less or equal sign. So this is A, this is X, this is B, and I'll call this like the tradition here is to call this vector C. Okay. Okay. Oops. Well, C. Like let's just call it C. Okay. So far, so good, everyone with me, like how I turned that into like matrix format. And again, I'll write some problems for you this week, and some of those will be kind of for you just to practice, like rewriting things into matrix versions and things like that, plus other stuff. Um, yeah, I'll kind of, I'll probably want you also to set up some optimization problems, like just like word problems, but you'll see what I'll do. Okay, so this was the original problem. So I'll kind of write this like separately. So this was A. In the original problem, this was the matrix A. The vector B was this. And the vector C was 1.2, comma 1.7. Which, well, I guess I could write it as a column vector if I wanted to. Like I would write it as a column vector actually, just to be a bit more consistent. Like whether I'm writing, like usually most of the times I'll think of the vectors as being column vectors. So that's good. Okay. Now, what's kind of fun that happens is what happens when you rewrite the other system in matrix format. That's where like the kind of aha moment occurs. So let me see if I can do that. Let me copy paste. Sorry, give me a second to copy paste like copy paste. Okay. Again, I'll share the notes. But let me kind of let's try to write this in matrix format. Okay. So if you write this in matrix format, again, oops, I hate that this goes so low. So if you want to write this in matrix format, the first thing you should do is rewrite this as a dot product. So write it as minimum of 3,000, 4,000, 5,000 dot y1, y2, y3. Okay. And again, like the first three conditions, if I want, I can assemble them into a single vector. So I can say that 0, 0, 0 is less or equal to y1, y2, y3. That's kind of like useful. And kind of like now I have two inequalities, right? I have two inequalities and three variables, right? So two inequalities, three variables is 2 by 3. So I'll put it like this. 1.2, 1.7 less or equal than, okay, so like again, like you want to extract a matrix from here, right? So this should be like a 2 by 3 matrix. This is 3 by 1, this is like 2 by 1, so that makes sense. And so what are, like, it's just like the coefficients, like it's 1 for y1, 0 for y2, 1 for y3. So this is 1, 0, 1. And then 0 for y1, 1 for y2, and y for y3. So this is 0, 1, 1. Interesting about how I found the matrices and everything. Okay, so where is the cool thing? The cool thing is that these things are actually related to the stuff that we found before. So let's like to the original problem. What is 3,000, 4,000, 5,000 in the original problem? Go back. Actually, let me write them like. So what is 3,000, 4,000, 5,000? That is literally the vector that I was calling B before. This is the vector B. So the vector B is appearing here. And again, it's kind of like useful to notice what happened, in the original problem, B, like, in the original problem, B does not appear in the function that you're trying to maximize. It appears more like in the matrix inequality, right? So kind of like that is being swapped of position, and instead of like appearing in the matrix inequality, it is appearing now in the function that you are minimizing now. So now B gets there. How about this one? This is also easy to kind of like see what that should be. What is 1.2, 1.7? That's literally the vector C, right? The vector C from before. So again, now this is like appearing in a matrix inequality, whereas before this vector that I called C was appearing in the coefficients of like the maximizing function. But I left kind of like the coolest thing for like last. What is, oops, oh my God, like, sorry about like the display. What is this matrix in terms of the original one? No one recognizes it. Sorry, I don't know if everyone can see it. This is like the original matrix. Oh yeah. Right, like, but how is this related to A?
Say transpose.
It is a transpose of the matrix. Like I swapped the rows into the columns. So, and in fact, I swapped the sizes because if you remember, like the transpose changes like the row, like the size of like the matrix, like, swaps rows with columns. So this is actually a transpose. So like maybe I'll put them kind of like side by side. So before we had the max of C dot X where like X had to be non-negative. Again, this is kind of like the vector. And you had A times X is less or equal to B. So this is like the original problem. And now in the new one, which is actually called the dual, but it's called the dual problem. Now you have the mean, not of C, so of B dot Y. Okay. And then the vector Y has to be non-negative. And here, like the inequality is that, you know, that C is less or equal to A transpose Y. So, like, they're kind of related because the idea is that, it's kind of like essentially the same vectors, but you're using them in different ways. So, like in the original problem, C appears in the function, but then appears in the inequality. And in the original problem, B appears in the inequality, but now it appears in the function. And the max becomes a mean, right? So you change max into mean, and you change less or equal to into greater or equal to. So like you kind of like everything gets reversed. So it's kind of like a mirror image in a sense of like, I mean, if you don't like the word dual, you know, because it's kind of like it has like several meanings in mathematics. It is kind of like a mirror image where you kind of like swap around the roles that the vectors are playing, and you know, he's like, and then like like you just like rearrange them in a different way, and the matrix gets transposed, which is also like the cool thing. Is that making sense how I went from one of the systems to the other? Yeah.
Um, I just had a question about like when we minimize the problem, like,
Uh-huh.
were we automatically supposed to know like how to minimize it, or it was just kind of like,
Oh no, so like for either whether it's a max or a min, there will be this thing called the simplex method that will say how to do it like as an algorithm, kind of like similar to Gauss-Jordan reduction of matrices. So it will have like the same kind of, there will be kind of like a same strategy for either of these. But yeah, that's kind of what I'll talk about in maybe 2 or 3 classes, like how to maximize or minimize. But the idea is like, yeah, you don't want to kind of like do what I did last time, where you just find the corners, because basically finding the corners can be a hard problem if there are like enough inequalities, like you don't, it can be hard to like understand. But yeah, there is like an algorithm that will say how to do it. And that is kind of like the only algorithm, I mean, not the only algorithm, but it's kind of like the algorithm that gets used over and over and over in this class, in the same way in which reducing matrices is what you did over and over and over in linear algebra. So it's kind of like the analog of that.
oh, okay,
Yeah.
and like, is there a reason, like mathematically, like why that makes sense? Like the original and then the dual problem, like is there like a proof that?
Well, like what I will prove later, which is what I was going to write, is that again, like provided the max and the mean are finite, because sometimes again you can have like silly situations where one is called unbounded, where one gives you infinite or negative, like silly things. But provided like the max and the mean are achieved, let's call it like that, then they have to coincide. Like that's kind of like the cool thing about like that's how they're related. They're like the max of the original problem, which is also called the primal problem, by the way. Like but again, like I don't want to kind of bombard you with a lot of terminology right now, but I'll just call it original for now. But like if you check the textbooks or like any place in linear optimization, that's called the primal problem, and this one is called the dual problem. And so like the big theorem, which I'll tell you about, but I just wanted to do it like in an example first, where you kind of like kind of with the farm stuff, because you can see all the details there. But the big theorem, one of the big theorems, like in the course, called like the duality theorem. And like, it's like, think about it like I'll write it in again, like verbally in a somewhat imprecise way, but later we'll be more precise. But it says it like, if the max mean to these problems are finite, well, are like, yeah, are finite, then they coincide, basically. In fact, like it's a bit better than that. I mean, because like the idea is like these values are always larger than these values. In fact, like fact. But again, I don't want to kind of get into like all those details for now. Um, which is kind of what we were seeing in our example, like the bounds that we were getting in the minimum problem were like the bounds that we were getting from the inequalities were always above 8,000. So what this is saying is that you can never go below the max. Like every bound that you would get from here is always above the max. And when in the minimum, they kind of match. And that actually is used a lot in practice because that is like an easy way to certify that you found like a max or a mean to the problem. Because imagine maybe you don't know if you made a mistake when you were finding the solutions. If you tell me, oh, I think I found the max to this problem and I found the mean to this problem, and they happen to give you the same quantity values for the like the expressions, then you know you're good to go. And that actually is important because again, like these problems, like in practice, like they can involve thousands of variables, like many of them do. So like there are always random errors and other things in computer algorithms, like so like it is good to have like alternative ways rather than just run the algorithm a second time to check that something is the correct solution. So it would be like, oh, solve the original problem and the dual problem, and if the spits out the same value for the function, like what you were optimizing, then you know that you were good to go, and there were no like bugs in your algorithm or things like that. So it's kind of like one of like the main ideas behind that is one of the main like things that makes like this topic like interesting, that you do have like kind of like this back and forth. In fact, I mean, and again, we'll get to those properties later, but I don't know if you remember like the transpose of the transpose is A, right? Like doing the transpose twice gives you back the original matrix. So like in a sense, which again, I'll explain later, if you forgot that this is kind of like came associated to this problem, and I just give you this problem like as the original problem, and you find it's dual, then you will get this one. So it's kind of like goes back to, it is really more like a mirror image. So think of the mirror of this is this, and so if you take the mirror of this, you get back to the original one. So like it's all, that's why it's called duality. Like in mathematics, when you talk about a duality, you mean kind of like an operation that has like a like a correspond, like a twin of sorts, like, or and then when you look at the twin of the twin, you get back to where you started, kind of. So like what this will say, the region problem. But again, like all those details I'll give you later. I just wanted to kind of like give you a sense of like what's supposed to happen with these things. That okay? Is that making sense? Are there any questions about this? So far, so good. Okay, so now I can kind of like explain where we're headed, just to kind of like give you like a better like idea of what this like the goal is. So what are like the next steps? Like as I had said before, like finding the corners can take a lot of time, but that's like, because there can be exponentially many corners, like the number of corners can grow exponentially with the number of inequalities and variables that you have. So finding the corners directly can be tricky, can take a lot of time, cannot be realistic, may not be realistic. So we will discuss like an algorithm called the simplex method that allows us to find the max in a more efficient way. So we will discuss like an algorithm to find the max or the mean in a more efficient way. Called the simplex method. Okay, so just to kind of again make it like as a table. I think I have it here. Let me see. So like this is kind of like good like an analogy to have in mind. So so if you have linear algebra, like if you think of the course like linear algebra, right? Like 250. And you think versus our current course, right? Like linear optimization. I think this is 354 if I'm not mistaken. So so again, like in linear algebra, what's the basic problem like that you're trying to solve, like the main problem? That you deal with most of the time, they are just equalities, like something like ax equals b. Most of the things in linear algebra that you do can always be rewritten in a way that you end up solving like an inequality of this sort. Like, sometimes it is more clever than others, you know, um, but you're trying to solve this, right? In linear optimization, what is the main problem? We're not trying to solve like a system of equations per se. We're trying to find a max or a mean. That's why it's called like the optimization. I'll just write it in terms of the max. So we're trying to find the max of like you're trying to find a max of a dot product, right? Like that's what I said is happening. I'll write it this way, right? And the idea is that x, like the vector x, satisfies some inequalities that more or less look like this. So where x satisfies so in a sense, like in the way in which linear algebra depends on, it's more about equations, like linear optimization has to do more with inequalities and like max being problems. Okay, so that is and again, most of like, in fact, I think maybe basically all the problems that we'll do in this class will always fall into this category, maybe with like a mean, like, some very small cosmetic change, like differences, but more or less like kind of like always like this. So that is how the main two problems like for each class corresponds to. Then what is the main technique for solving each problem? So like again, in terms of like techniques, um is in linear algebra is basically row reduction or like this Gauss-Jordan like reduction method, right? Like so row reducing the matrix, right? Which again is sometimes called Gauss-Jordan. Row reduction, let me call it like that. And what I was just saying is that instead of like Gauss-Jordan or row reduction, what like the thing that replaces that in this class is more like this simplex method, whatever it is. So that's kind of like what corresponds to that. Okay. And then the other thing that happens in linear algebra is like kind of what is the main like here like you're studying equations, right? But what is the main way to understand like systems of equations like many times is like using vector spaces. So like like the object that this is related to in linear algebra um, is like a vector space. So for example, um, I don't know if you remember this stuff, but this has a solution if the vector B belongs to the column space of the matrix A. Like, there are many things that you can say in terms of like, once you have like the language vector spaces, there are many things like about the systems of equations that can be just specified in terms of like the vector space. Okay. So kind of like the most important thing in linear algebra in terms of an object that you're studying are vector spaces. And kind of like the thing that replaces like the vector spaces in this case is what you call like a polyhedra, which is actually what I'll start telling you more about next time. Which are sorry, I don't think it's kind of like looks super clean. So it's called like a polyhedra. Okay. And what it matters about these things, which is what I will tell you about next time, is that they are convex, whatever that means, and that's what I'll explain next time. But convexity is kind of like the thing. Convexity is kind of like the thing that makes a lot of this stuff like really work nicely. So we do have to talk a little bit about convexity and what that means before once we have discussed what convexity is, like then I can tell you the simplex method. That would take me probably like a week or so. Okay. But this is kind of like a good table to keep on the back of your heads because it's kind of like a compare and contrast between the two things. So like just think about like these polyhedra. Polyhedra were like kind of like this, like the image that I showed you earlier today. That was like a polyhedra. Or like the thing from last time. So those things are called polyhedra. But the important thing about them is that they're convex sets, and so I have to tell you what convexity is, which is one of like the more important, like useful properties in mathematics to have for like applications and things like that. So like the only thing I'll finish to wrap up today's class, because it's like takes like 2 minutes, but it's like a very cute like proof. I don't like, so what I mentioned to you last time, like, is that if you were trying to find the max or the mean of a function, right, like this, it can only take place like at the corners of the region, right? There is like a very easy way to see that using calculus, but I'll do it just using linear algebra because I'm not that's why not everyone can take a multivariable, so like I'm not going to do it that way. So I'll just kind of like explain that for a bit because it's kind of like a good thing to remember. Just like before doing it, that also it's useful because it gives me like an excuse to remind you about the dot product. So just like a quick review of the dot product. If you had two vectors, x1, x2, x3, up to xn, and you have another vector y1, y2, y3, up to yn, right? What was their dot product? The idea of the dot product is that, you multiply their entries. So you multiply the first entries together, the second entries together, the third entries together, and so on. And then you have, sorry, that should have been a y1. Okay, everyone hopefully remembers that formula. Two things to remember about what's useful about the dot product is that if the dot product happened to be zero, you call the vectors perpendicular or orthogonal, right? So x dot y, well, also, that x dot y is the same as y dot x. That's also important to remember. And also if x dot y equals zero, then like the number zero, then the vectors are like orthogonal or perpendicular, depending on how you want to call them, are orthogonal. Right, and the other thing, which is what I'm about to use for a moment, is that if let me draw the vectors for a second. If you have like the vector x here and you have the vector y here, if there's like an angle between the vectors, like there's like a very useful formula for the dot product in terms of the angle, which is like the product of the lengths of the vectors or their magnitudes, which is like the other name that's given to this, times the cosine of the angle between them. So here, like again, I don't know if trying sometimes like I'm trying to remind you of like the basics as we go along because I'm not super, sometimes like those are things that are easy to forget. So like the dot product, like a more geometric way to find it is like the product of the lengths of the vectors times the cosine of the angle. Is that okay? Is that making sense? Everyone with me so far, so good. Okay, so the last thing I want to say for today, which is really cute, again, like I mentioned last time, but at least I'll give you like an idea of why, um, like a more like special case of it is that imagine that you have like a function. Okay. So like here's like an like important thing to know. So like important. So you're trying to find the max of c dot x. Again, this is like c1 x1 plus c2 x2 plus c3 x3 plus cn xn, where x is constrained to be inside of a region R. Let's call like the region R for now. So what I'm trying to say is like imagine like I'll draw the picture in 3 dimensions because like that's the best I can do. Let's say x1, x2, x3, x3. So like I'm saying like imagine you had like a region R. Okay, and you're trying to find the max of this expression, right? You're trying to find the max of this expression but x is forced to be inside this region. By that, I just mean that the vector x like has to be somewhere inside this region. So like the vector x terminates at the inside the region R. So again, like we're trying to maximize this function, but like you can only choose x, like x to like the vectors that you choose for x like have to be somewhere inside of R. So like C is supposed to be known, like C1, C2 up to Cn, like they're known, like the variables are x1, x2 up to xn. Okay, so what we saw last time is like the max could only occur at the corners. Like in this picture, like they're not necessarily clear that it can be at the corners. So what I'll do kind of show you for now is that the max has to occur along the boundary of the region. So it cannot occur on the inside. So what I want to show you now is that the max occurs along the edges of the region, along the one of the edges or boundaries of the region. So what I'm trying to say is like there's no way for this vector to be the max. The vector, like the max would need to occur either here or here or here or here or here or here or here. So we're on the edge. It cannot be anywhere inside. So like, is that making sense what I'm trying to like say? So like the max cannot be on the inside of like any region.
Professor, why is that again?
Sorry?
Why can't it occur in the?
Oh, that's what I'm about to explain. Yeah. But like, I'm just trying to explain the claim that I'm saying, like, if you said, oh, the max is here, I'm saying, oh, that cannot happen because it's on the inside of the region. Like, it can only be on like, like the shell, like of like the exterior, why? It's actually cute. Like, so it's what someone had asked me like if there are proofs in this class, and I was saying like last time there are not really many proofs in this class, but they're like what I like to call like 1 or 2 line proofs. So this is one of or 2 line proofs. So this is kind of like the type of thing that I would expect you to know how to do, but I'll give you like a list of problems of this sort for you to practice. But is what you would like, what people sometimes call like a proof by contradiction. So I'll kind of like show you how it works. Imagine that you said, like, so I'll just say like, imagine like the max occurs at the inside, on the inside, happens on the inside of the inside of R. And I'm almost done, but you'll see it's like a very clever like proof. So I'm saying, oh, okay, my claim is that the max is this vector. Right? That's what I'm saying. Okay, I think the max occurred on the inside, somewhere in here. Okay, and about to tell you this cannot be true, right? Why this cannot be true? Because well, remember we have this vector C that's the one we're taking the dot product with. I don't know where that vector is located. It doesn't really matter, you know. Let's put it somewhere in here. I don't know where C is, you know, but there's an angle between these two vectors, right? So what is C dot like this, like maximum where you're saying that this is supposed to happen? Well, that is like the product of the lengths of the vectors, right? Times the cosine of the angle. So far, so good, everyone with me? Now, what is, and here's like the clever part, which is, what does it mean to be on the inside? When you say that you, oh, this is so cute because I do have my pointers. When you say that you are on the inside, that means is that you can move a little bit in the direction of the vector and you still remain on the inside. Otherwise, you know, that is something you can definitely not do on the edge, right? If you're at the edge, you move a little bit, there you're already outside the region, right? But when you're on the inside, almost by definition, actually, being on the inside means that you move a little bit and you're still on the inside. Like, I mean, otherwise, like this wouldn't work. So if I move a little bit in the direction of this vector, where did I leave my pointer? Imagine I move a little bit in like I'll copy paste the picture just to not make it like super messy, you know. You like just move a tiny amount, like let's call this like x new, like, you know, this is like a new vector, right? Well, what is the dot product between these two? You know, this is still like the product of the lengths, right? And I mean, kind of like, if it's a mess if I kind of had drawn it literally on top of the other one, but you are supposed to think that it is like just like an extension of the blue one. So the angle is still the same, right? So it is the same angle. So these two quantities are the same as before, right? So this is the same as this is the same, these two things like agree. So what is the difference between these two products? Like only the difference in the lengths of the vectors, but I increase this a tiny amount. So this I already maximize, like I already increased the value of the function. So this product has to be larger than the previous one because this factor is larger, right? Larger factor. So is that clear? Isn't that clever? Like, so you increased a little bit the amount of the multiplication. Because by being, sorry about that, by being on the inside, you can move a little bit more in that direction. So that tells you, and then you kind of keep iterating that, like doing this again. So now you're here, you increase the value, move a little bit more in that direction, move a little bit more in that direction, move a little bit more in that direction, and then you hit the edge, and then you're done. Like, and that is where the max should occur. The same goes with the mean. If you were doing like a mean, but then you shrink, right? Like you shrink, and then you hit like an edge. So it's like a very clever proof. You know, if you wanted to do like the multivariable proof, it is kind of like the gradient of a linear function never vanishes, and then you're done. Then that's it. But it's kind of like nice to have like a proof that's only like in terms of like linear algebra. Yeah.
So does cosine theta be cosine theta plus d theta?
Plus, well, this is like the angle between the two vectors, right?
Yeah.
There's like these two are completely parallel, right? Yeah, like it's just like, you know, if I draw them, it literally one on top of the other, it kind of like loses a little bit of the point of the picture. Okay, let's finish here. So as I said, like I'll try to write some problems for you to work on in the next few days. Try to have them ready either tomorrow or Thursday, the latest. And then when we meet on Wednesday, I'll tell you about this convexity stuff, which is what we need to before like getting into the details of the simplex method. But I think this is like a good place to end. Okay. The region in this case doesn't have to be flat. Like that's why I literally do it on purpose so that it will look curved. Yeah, yeah. It can be any random region. Like
It doesn't even to be convex.
right, it doesn't even need to be convex. Like that's like right. Yeah, exactly. That's why I do it in this way. You can have like yeah. It doesn't matter how it looks like. Okay. Yeah.
Where's the number C?
Well, I mean, it depends. Like, the thing. You're talking about this one.
Yeah.
Like the thing is like, when I was trying. Sorry, just to go back to the for a second. Like when we're trying to maximize the dot product, right? So this is like the one that you can kind of change. This is like given to you, right? But I just don't know where it is, so I had to draw it somewhere. So like you could have drawn it here or whatever. Like it doesn't matter. It's kind of like the same proof, like
In the modern day,
Correct. And then you would, you would place it somewhere. Yeah. You too.
There are reference for this, but like,
Okay. So yes and no. I mean, this part like about the. Oh no, like